In this video lecture, we will start with modified Euler's method, which is also famous to solve first order ordinary differential equation like the previous method we studied named Euler's method. This method has got several names like Eulers method, Cauchy method, improved Euler's method, improved Euler-Cauchy method or Predictor-Corrector method. The last name is based upon its nature, how we are going to implement this method. Okay. In a simple language, we can say that it's every approximation is rectified again and again. Okay. That means if y1 is the first approximation, then y11 is first better approximation, y12 is the second better approximation, and so on. This process goes on till the stability in first approximation is achieved. So this is quite important, and this process up to the stability of the first approximation is called stage 1. Okay. In the same way, we will proceed for second and higher approximations to reach to the desired accuracy. Okay. Now let's go through the technical terms involved here. Let's see this first expression. This is nothing but normal Euler's method formula, which is known as predictor formula. So predictor formula will give you y1 which is equal to y0 plus h times f evaluated at x0 y0. Okay. So here only one slope occurs in Euler's formula, whereas in the case of modified Euler's method, what we are going to do now? We are doing better and better approximations for y1 at first moment. Okay. So this formula is known as corrector formula, and the process to find the correction in this formula is we are changing here the slopes. Okay. Instead of single slope, we are now preferring mean of slopes. The mean of slopes means here the f of x0 y0 term is there, but along with that there is another term which is added here, that is f x0 plus h comma y1. Okay, and then divide by 2 will lead to the formula. So it is same as this one. Just see here, this is nothing but our first better approximation, which is equal to y0, that is initial approximation, plus h times f x0 y0 plus f x0 plus h y1 divided by 2. This x0 plus h is basically x1. Okay, so this is x1 comma y1. So I am just taking mean of slopes of these two entities. Okay, the next stage is to get second better approximation, and how do we get that? That is y12 which is equal to y0 same plus h by 2 f x0 y0 plus f x0 plus h comma y1 1. So notice this change here, instead of normal y1 now I am preferring y1 1, right? So here I am getting a second better approximation, and then I will go for the third better approximation y13, which can be obtained by using y12 here, and so on. Okay. So we will continue this process till the desired number of stages are required and desired accuracy is achieved. For example, fourth refined approximation is considerable, then we are going to use it in the stage 2 as an initial approximation. So this is important, and let's see how. So for example, stage 2. Now y14 is our considered thing for the sake of understanding. So what will be my predictor expression? This is my predictor expression. I am just writing here predictor. Predictor expression y2 is y14 plus h fx plus x0 plus h y14, right, which is same as y14 plus h f x1 y14. Now the first better approximation of this second approximation y2 is given by y21 is equal to y14 plus h by 2 f x1 y14 plus f x0 plus 2h y2. Now see, initially I have this y2 that I am writing here. Okay, this is my first better approximation. Naturally the second better approximation will go with the uses of this y21 here. Okay, so I am just writing here that in continuing in the same way we are getting better and better approximations for y2. right? So I hope with this you have got an idea that how we are basically preparing our stages, and then we are working with the higher and higher desired desired result with accuracy. Okay, so this completes our stage 2. In the same way, continue for finding higher approximations till the desired accuracy is reached. Let's digest the method through one problem. Okay, now let's see the problem. Using modified Euler's method, find an approximate value of y when x is equal to 0.3, given that dy by dx, which is equal to f of xy, which is x plus y, and y equal to 1 when x equal to 0. Clear? Let us write down what we have and what we want to achieve. We are given the value of y equal to 1 when x equal to 0, that is y naught. Obviously, this is my initial approximation. Okay, we have fxy equal to x plus y. We are asked to find y at 0.3, right? Now we have several approaches here. I am quickly showing you these approaches. We are going to consider h is equal to 0.1, and hence our process will be 3-stage process. We can also start with h is equal to 0.05 and may proceed with a bit lengthy calculation, obviously. Okay. If we are asked to find y at 0.6, suppose this is the modification in our problem, then we may think of considering h is equal to 0.2 and then you may proceed further. Okay. So for a while we will go with first possibility. So consider h is equal to 0.1. Hence we have chosen to dive into 3-stage process. Let's write down every detail. dy by dx equal to fxy, which is equal to x plus y. First thing, y at 0 is equal to y0, which is equal to 1, where obviously x not equal to 0, that is second thing, and h is equal to 0.1, that is third thing, and y at 0.3 is asked. Okay, so basically I am just noting down, this is my first thing, this is my second thing, this is my third thing, and this is my fourth thing. Fourth thing is nothing but a target. Okay, so here y is of course an approximate solution to the given differential equation, right? So this is the thing that we have done so far. Now for the sake of simplicity, I have prepared fully worked out table here, and let's discuss the table thoroughly so that you will have a proper idea about the working style of this method. Okay, so I am just narrating here the number of stages. Obviously we are starting from 0.0 and we are having an increment of 0.1. So obviously this process will give me 3 stages. Okay, so I am just writing here that h is equal to 0.1 and x naught is equal to 0. We want to reach to 0.3, and hence 0.1 will be first stage, 0.2 will be second stage, and 0.3 will be third stage. Okay, so these are the stages, and hence I am just calling this method for this particular problem as 3 stages problem. So stage number 1, x is equal to 0.0. Obviously this is the starting point. I am just writing here 0 as 0.0. So fxy equal to x plus y is equal to y dash. Now what is x? X is 0. What is y? Y at 0 is equal to 1. This is given to me. Y at 0 equal to 1. So I am using this one here, which is equal to 1 obviously. But this color boxed expression 1 and this colored expression both are different because I am going to use this entity somewhere else. Okay. Okay, for the sake of convenience, I am writing here mean slope as dash because for the first starting part we will not have 2 slopes. Okay, so we are going to use the same slope which we are writing here. See, this one is nothing but slope. Okay, so this old y, that is 1. So here just mark this colored expression box. So this one is same as this one, old y. Okay, plus h is always there, which is 0.1. So this is my step size 0.1 and into mean slope. Now this one is nothing but this one, this blued one. So just mark it here. So I am just writing here this one, which is nothing but a mean slope itself, and hence mean slope is 1, right? And the final answer is 1.1 in this case. That 1.1 carried forward here. Okay, obviously now you have made some increment in x, and that is with 0.1, this one. So 0.1, 0.1 plus 1.1, that 1.1 is this one, so mark here the green box 1.1, which is equal to 1.2 is the addition of these two entities. So this is my new slope now. So old slope is this one plus new slope. So 1 plus 1.2 divided by 2. This is going to give me a mean slope. So just mark this light blue boxed expression. The output of this expression is 1.1 that I am going to use here. Fine. So 1 again old y, which is constant throughout the stage 1. So 1 plus 0.1 into this 1.1, which is equal to 1.11, right? Now just 1.11 you see, I am just carrying forward here, 0.1 is obviously there. Okay, so you can see here, this is my first approximation, this is my first better approximation, and this is my second better approximation of the first one, right? So in this way I am going further. So what I am going to write here, this 1.21, that 1.21 is the same entity which I am writing here. Again this is my old slope, so old slope plus new slope, and this is 1 by 2, I mean divided by 2. That will lead to me this entity 1.105, right? So 1 plus 0.1 into 1.105 is equal to this one. Okay, just continue in this way. I am getting the fourth row here. Okay, now what happens, basically if you just observe these entities, this is 1.1105 and this is also 1.1105, right? So correct up to 4 decimal places, you can say that these two entities are correct, and hence I can say that I have achieved good accuracy in stage 1. So I will stop here regarding stage 1 and I will enter into stage 2. Stage 2 has the starting point of x as 0.1. 1.2105 is my value of y which I have obtained here. Okay, that is this one 1.2105. Okay, so basically this one 1.1105 plus 0.1, that is 1.2105, and then now my old y becomes this one 1.1105, right, plus 0.1 and then 1.2105, which is equal to 1.2316. That 1.2316 will be here, and now one increment of 0.1, so I am starting here with 0.2 now. Okay, so this is my second approximation 0.2 and then I am just doing the same process 1.1105, 0.1 into this one, this whole quantity you see here, it is going to give me this value 1.3211 that I am writing here. Okay, which is equal to 1.2426. That 1.2426 plus 0.2, okay, will give me 1.4426. And again, if you simplify these expressions, you will get this one. Mark here that these two entities are having accuracy of 4 decimal places, so I can stop in stage 2 as well, and now I can go for stage 3. Okay, where the starting point of x is 0.2 and obviously y is 1.4432 that I have told you earlier, and mean slope which is same as 1.4432, and then 1.3875, that 1.3875 here being carried forward, and obviously the next value of x is 0.3 being added 0.1 to this 0.2, and then 1.4432 this entry plus 1.6, that is addition of these two, that 1.6875 is this one. You will get the answer. That answer is 1.5654 that you need to use here. Okay, this answer. And then 1.2432, this one, this entity is my old y, right? So this is 1.2432, and then I am getting the higher and higher entries 1.3875, just we discussed here, and then the answer is 1.3997. Again use it here and then proceed further and mark these two approximations, and they are having the accuracy of again correct up to, I mean accuracy of 4 decimal places. Okay, so we can stop here in stage 3, and finally you can say that the correct answer or the desired answer or the required approximation for your problem or differential equation is 1.4004, right? And this is the answer that I have achieved through modified Euler's method or predictor-corrector method. So I hope with this video you will be able to understand the thorough idea about modified Euler's method and how to implement it. Thank you. Once again, let me tell you that based upon this understanding, you need to understand very well that how to work out with such kind of problems. So please do hard work and work out as many problems as you can so that you will have a full idea about this method. Thanks a lot.